is this loud enough? So hi, I'm Fiona McCluskey. I'm a grad student at UC Davis working with Andy Webpool. I will kind of preface this by saying I've been quite sick this week, and so I've missed a lot of talk, and it's going to be very sad. But also not all mentally or physically here right now, so please don't laugh at my talk too much. But yeah, today I'm going to be talking about, as the title might state, stellar kinematics in Milky Way-like galaxies and entire spaces. So stellar kinematics are particularly interesting if stars have really good gravity. So a star's present-day orbit is set by both whatever orbit it initially formed on, but also all the gravitational encounters it has with life. That means we can use stars or the orbits of different stars to learn about if any state of star formed by them over time. That's what sets the orbit. We can also learn about the nature of different interactions the star has with lifetime. So whether that be with structures Jesus, stars, spiral arms, DMCs, but also things like mergers and satellite interactions that can affect the star's kinematics. This is generally called dynamic heating. So, what makes the dynamic state of the star forming out of them so interesting? Well, that's because galaxies tend to evolve a lot over time. We know that in the very early ages of the universe, galaxies are not the nice Milky Way-like disks that we see today. They're these weird toroidal, less massive, bursty structures that gradually over time form into disks. The initial disks are thick and turbulent, but as we go on, we get the nice Milky Way thin disk that we see today. But especially with JWST finding a lot more thin rotating disks than we expected at really high redshift, there's still a lot of questions about this process. And this is generally dubbed successful. There's also a lot of other things that we need to learn about using stellar orbits. Things like mergers, starbursts, gas accretion, all things that are going to set kinematics that stars form with and how they change over time, and this can help us learn about galaxies. So, the Milky Way, we live in it, and has a lot of stars, and we can study it pretty well. And there's been many large surveys, whether that be spectroscopic surveys, and then Gaia, that is now giving us a lot of information about our home. So one way that we can study these processes in the Milky Way is something called the age-velocity dispersion relationship. This has been studied going back to the 1940s. But this is just if you take stars in the solar nuclid, spin them by age, and then look at their velocity dispersion, which is a measure of their rate. You see that there's a pretty strong increase with age. So as we get older, stars' motions get more and more chaotic. They start nice and distant. By the time we get to like 10 billion years, they're going at a good rate. So one issue in interpreting this, though, is that we don't necessarily know how stars form. So maybe a star forms kinetically cold and then was heated a whole bunch. But it's also possible that to form this burst in toroidal system, it formed hot, it was heated only a little bit. It's hard just by looking at the stars in the Milky Way to have a full picture of how this galaxy is. So we want to be able to understand the Milky Way in a cosmological context. The Milky Way is just one galaxy. It's a nice one, but still only a handful of one. So it's hard to kind of learn about if we're learning about like capital G galactic evolution or galactic evolution in general. So there's still a lot of questions. When and how did the Milky Way form? Is the Milky Way even standard for galaxies of its mass? And then if it is or not standard, how close to the background do they think they are? There's lots of questions. So one way we can study this is trying to look at the kinematics of other stars in nearby galaxies. The Milky Way, a lot of friends, it lives in the local group. So we don't really have to go over this too much, but we have M31, more mass than the Milky Way, and unlike the Milky Way, which likely had its most massive features, like 8 billion years ago and has 2 comets since then, they think that M31 probably had a major merger about 2 to 3 billion years ago. So we can look at M31 to learn about the impact of mergers. And we have M33, a nice little satellite of M31. This is on its first infall into the local group. And we can use M33 to learn about the formation of lower mass galaxies. Not only that, thanks to the famed New survey, we now have a stellar kinematics for 19 star-forming Milky Way mass galaxies in the nearby. So now I'm just taking data from the literature and plotting the velocity dispersion of stars versus age, as we saw in that plot a couple of times ago. So this is just a broad range of values that is observed in the literature for the Milky Way. This is M31 and M33. So they're quite a bit kinematically hotter. They have less rotational kinematics than the Milky Way. And this is the data from Phanes. So just looking at this, it kind of looks like the Milky Way is kinematically colder than a lot of the other nearby galaxies. How can we study this even more? Well, as you might guess from what I was in my talk title, you can look at the Fire-Sea simulations. You've heard about them. What makes these nice is, one, we have pretty good statistics in that we have 14 galaxies. So kind of like how we now have 24 tree-like galaxies to resolve ages and stellar kinematics. Now we have 14 type galaxies to learn about these different cosmological histories. And because with the resolution, we can resolve the star forming ISM and learn about the processes that scatter stars that produce. So, how does fire compare to M31, M33, and Phanes? So these dots, these fire points are the observed data, and this is fire when that's age thinning, inclination, spatial extent of the observations. And I think that shows pretty good agreement. M33, I think that's also pretty good. Phanes, on the low age side, fire is a little bit colder, so this is probably just coming from the fact that it's an IFU survey, has limited spectral resolution, and also the light that we're getting from stubs for young stars probably has some microscopic for slightly older stars as well. So, pretty good. So, the question's asked, how does this compare to the Milky Way? So, here I'm just showing every component instead of just the one age velocity dispersion. But this is fire, this is the median for fire, this is the Milky Way. So it seems that we're not quite matching it. So on average, we're considerably hotter. But what all these little kind of hard dots will see are individual solar neighborhoods of the Milky Way mass galaxies in the simulation. And when we look at individual patches, we do have some agreement. But overall, we are hot. So why might this be? One reason might be that the Milky Way stellar disk formed abnormally early for a galaxy that's mass like zero. So this is taking all the M12 from the isolated galaxies in fire simulation. When did their disks form? And what are the current kinematics that they have today? You see a general trend that disks that formed earlier have colder kinematics today. They're more rotational, less first dominated. And also put the level groups. These tend to actually form a little bit earlier, related to why the Milky Way formed earlier, because this environment assembled a mass a bit earlier. And this is a remarkably strong correlation between the age of this onset and how cold we are. The earlier it is formed in the galaxy, the colder it is at that time. And if we extrapolate and put the Milky Way's value, it kind of indicates that it formed earlier than all our galaxies, so probably like 12 gigayears ago, which is actually in line with recent observations from the past couple years. This year, the Milky Way disk really did start to form, maybe only a year or two after the Big Bang. And I just want to note, this isn't just a fire thing, that the Milky Way is so much colder than our galaxies. This is true for Auriga. This is all their initial simulations. This is a weird one that has a really weird equation of state. Don't worry about it. But consistently, they're hotter than the Milky Way. This is from the Deems, who gave a lovely talk on Tuesday's paper. And this is looking at the time that the metallicity that different galaxies in electric TNT systems spun up. And the Milky Way seems to spin up about earlier than 90% of similar mass galaxies in electric TNT. And then this is looking at kinematics from about 500 Milky Way mass galaxies from manga. Milky Way, M31, M33, the general manga relationship. So this isn't just me being, oh, we don't match, so therefore the Milky Way is weird. There might actually be a consistent story here. So if we can say that fire has relatively accurate kinematics, maybe, then we can start to learn things about their kinematics using the simulations and not be super duper worried. So this is just a quick little thing to say. How do different age errors impact the velocity dispersion relation? Ages are really hard to measure accurately, especially for old stars. So this is if we just had perfect age information. And there's a nice big merger here. And it has a really clear spike. Now we put in 5% age uncertainties. That's down a little bit. By 10, it's basically all gone. 20, 30, 40, and so forth. So 20% age uncertainty is kind of like the best you can get. Maybe individual stars can get down to like 5 or 10, but 20% is generally kind of what's very good. So if we have 20% age uncertainties, we don't see merger signatures, and we also see a different shape of this velocity system. And we don't have to worry about this. So to summarize, Milky Way, probably a little bit weird. Fire, probably not very weird. Earlier forming dips are pretty chilly. And the observability of past mergers requires
Omri Ginsburg from the Hebrew University. I have, so you showed at the beginning that older stars had higher vertical velocity dispersion. But did these stars form with a high velocity dispersion, or they got heated up by what you called initially dynamical heating?
So this is a slide I didn't show. So it depends on the age. But we do see that there is that young, very old stars in our galaxy form kind of cold. That's just set by the overall mass of the galaxy. And so it depends again on the age, but these stars form with a variety of different, and then are subsequently heated as well.
Thank you, awesome talk. So James and also showed that there was like one of the galaxies in far Romeo, which it was like forms disk very early, like Milky Way. So I was wondering if you compared this like velocity dispersions for this galaxy as well. Can it kind of explain the difference?
Yeah. So Romeo, I don't have the plot here, but I can show you during lunch. It does have, it's the earliest forming disk, and it generally has colder kinematics. It's the second coldest, though. There's another one that's colder, but I guess we go to. I believe that's. Or this is Romeo. I'm sorry. So.
Let's thank Fiona and all the speakers. And please don't forget to upload your slides. Enjoy lunch.